Hello students, welcome to this module which is part 2 of our series on basics of conditions at an interface. Basically we are talking about fluid interfaces. In this module what I am going to do is to illustrate how to write down the component wise equations for such systems, because in the previous module all the discussion was done in abstract vector notation. Here I'll try to tell you what are the issues involved in writing these conditions in terms of components. Let's first take normal velocity continuity. We said that v dot n for a phase change for a bound interface without phase change, v dot n in phase A is v dot n in phase B. Okay, let's imagine that you have an interface like this. Okay, and for simplicity I'm going to assume two-dimensional interfaces just to avoid writing x, y, z. I'll just write the xz plane. Many things can be easily generalized to three-dimensional interfaces as well. So the location of this interface is denoted by z is equal to h of xt. Okay, now let's call this phase A, let's call this phase B, and let's first assume that this is known. Although I told you in the previous module that the location of the interface itself has to be obtained by solving the kinematic condition. Okay, and so if we know this, then n can be calculated. Because we can write f of x z t is equal to z minus h of x t is 0, then n is grad f by mod grad f. Okay, so n can be written as nx ex plus nz ez after calculating n using this approach, right? You can find the components nx and nz. Okay, so v dot n becomes vx nx plus vz nz, and once you find n you can find t, because t is perpendicular to n, so you can easily find the unit vector t. Then v dot t is given by vx tx plus vy vz tz. Okay, now the stress is given by t dot n, and if you have a normal component you need n dot t dot n. So instead of x and y I'm going to assume x and z, I'm going to assume 1 and 2. Let's think of x as the direction 1, z as the direction 2, makes the writing easier. So plus n2 e2, the same equation, it's written in terms of 1 and 2. Okay, so I'm going to assume 2d again for simplicity, right? So the normal component of the stress is n dot t dot n. In index notation this is nothing but ni tij nj. Okay, where whenever you have a repeated index you have to sum over all the two directions. This essentially means that this is I is equal to 1 to 2, j is equal to 1 to 2, ni. Okay, so this means this is n1 t11 n1 plus n1 t12 n2 plus n2 t21 n1 plus n2 n2. Okay, now let's take the simplest case. This is 1, this is 2. That means that let's say the interface is flat, then n is e2. That means n1 is 0, n2 is 1. Okay, therefore n dot t dot n will be simply, all the other terms will be 0. Okay, this is 0, this is 0, this is 0, only this will be 1, t22. Okay, similarly we can find t dot n. This is nothing but in index notation ti, tij, nj. This is nothing but t1 plus t1 plus t2 okay. Therefore if I have a flat interface like before, let's call this 1, let's call this 2, okay, and this is t, this is n. Now t becomes e1, that is t1 is 1, t2 is 0. Now in this case this becomes t dot n is simply t1 2, because all the others will be 0, because you know that n1 is 0, n2 is 1, so n2 is 1, t1 is 1, so this is contributing. n1 is 0, t2 is 0, this is not contributing, and so on. Okay, so this is how one writes the components of various terms. Okay, of course if you have a more complex interface which is not a straight line, which you have t n, then of course n and t will keep changing and you have to write it in a more complete fashion, right? So all the terms will be non-zero in general if you have a more complicated interface. In 3 dimensions, if you want to know how it's going to look like, let's say an interface looks like this. So this is, let's say, 1, this is 2, the third direction is 3. Let n be equal to e3, let t1 is e1, and there are 2 tangents, remember, to a flat surface. Okay, now if you want to know what is n dot t dot n, which is ni, tij, nj, this is summation ij now going from 1 to 3, because there are 3 directions. It's a 3-dimensional system. So this is n1 t11 n1 plus n1 t12 n2 plus n1 t13 n3 plus n2 t21 n1 plus n2 t22 n2 plus n2 t23 n3 plus n3 t31 n1 plus n3 t32 n2 plus n3 t33 n3. Okay, now because the interface is flat, then n is e3, that means n3 is 1, n1 is 0, n2 is 0. So for this particular case, this entire expression will boil down to t33. Okay, now we have also for this particular case, t1 is simply along the one direction, it's e1, t2 is e2, so that means that only t11 is 1, here t22 is 1, right? All the others are 0, and t21 is 0, t31 is 0, here t1 of 2 is 0, t3 of 2 is 0. Using this, if I find out what is t1 dot t dot n, okay, if I expand this out, I'll get t11 t11 n1 plus t11 t12 n2 plus t11 t13 n3 plus t1 plus T2 1 T2 1 N1 plus T1 2 T2 2 N2 plus T1 2 T2 3 N3 plus T1 3 T3 1 N1 plus T1 3 plus T1 3. Okay, so now if I substitute that only T1 of 1 is 1 and N3 is 1, all the others are 0, then the only thing that is going to survive is T1 of 1 and N3. So this will give me T1 3. All the others are 0. Okay, so this is just to tell you how to write down all these equations, continuity conditions, in a given coordinate frame, because after all, when you solve a problem in hydrodynamic stability, you will have to write all these in a given coordinate frame. Okay, so I'll stop here, and in the next lecture I will start with next module I'll start with Rayleigh-Taylor instability, where we will use all these ideas as we go along. Thank you.